Welcome everybody with this advanced course on basic soft lens fitting. First off, I want to thank Carlos and the entire Consemac team for organizing another great class successful event. So thanks so much for doing that and spreading the word. Now what I want to do in this particular talk is actually do a little bit upgrade from last year. Last year we looked at soft lens fitting 2.0 in 2020. Now in 2021 I want to dig a little deeper if you want. Because to be quite frank, there's a little bit more to it than meets the eye. It's a little bit the tip of the iceberg. Let's dig a little bit deeper and look under the surface to see what's there to really understand what we're doing and what we're not doing, and how we can learn from that to actually upgrade soft lens fitting. Because that is the goal of the soft, and soft is survival of the fitting team. That's the purpose of the team, to look at that. It's a puzzle, and there may be a couple of things that we don't know, but there's a lot we actually do know. So let me walk you through that, and it starts with the ocular surface. What do we actually know about that? And then we're going to talk about contact lenses and everything related to it. So let's first take a look at the ocular surface and the methods used to do that. So in essence, what is our workbench? Well, when we talk about soft lens fitting, we're actually looking at a workbench of 15 millimeter. So that means a lens is 14.2 maybe, and then maybe 2.2, 0.3 millimeter movement on each side. So that's why we came up with the 15 millimeter as a benchmark. Now, if you look at the normal eye, this is roughly what the normal eye looks like. So corneal curvature, eccentricity, diameter. So this we can use to define, do we have a normal eye and should we be able to fit a normal lens, because we have better soft lens than we ever had. But sometimes you may want to go to a custom lens, but you don't know when you want to do that. And that is exactly where this comes in. But that's not the whole story. The ocular surface over a 15 millimeter cord is actually a little bit more complex than what we just looked at. It could be best defined as sagittal height. Is the sag the forgotten barometer, like this paper from 2016 from Johannesburg seems to imply? So what is sag? Let's take a look at that. So this paper explains it really well. It's not too complex to measure the sagittal height from a base chord, whatever chord you want to set, to the top of the curve. You take the curve of the what you want to measure and then the diameter, and that's it. So that's not too complex. It becomes a little bit more complex if you add in the flavor of eccentricity. So we know the cornea flattens from center towards the periphery, so if you want to add that, okay, then you can put that into the formula. Still overseeable. But then the cornea has a different curve and diameter than the part on the sclera. So you would have to calculate it twice basically, one on the cornea and one on the sclera, to get the full scope of that anterior ocular surface shape. To make it, well, not even more complex. In fact, it's simpler, but the recent studies we've done in the last 10 years basically at Pacific University looked at that transition from cornea to sclera, and what we found is that more often than not it's actually a straight line. It's a tangent, not a marked transition from cornea to sclera. All this comes from scleral lens fitting, of course, and in fact there are a couple of lens designs out there now, these are some publications, that actually use tangents in the periphery, or bitangents if you want to go toric. So can we use that information to better define the ocular surface? I think we do. Here's a beautiful picture from Damien Fisher, who just finished his PhD at the QUT in Brisbane, Australia. And what it shows beautifully, that's why I wanted to show it to you, is that the transition from cornea to sclera is in fact a straight line, because everything there is filled with epithelial cells. So if we assume that, and let's do that for now, then there's 5 basic parameters that define the ocular surface and the ocular surface shape that we can work with, and they're all listed here on the slide. Now, as I said, there's a couple of things we can do with this, and one is we can define the normal eye versus the non-normal eye. So if you have a normal bell curve of eyes like we see here, the x-axis is actually half quarts, that's normal eyes. And you know, on the left, on the right, these are either very shallow or very deep eyes. The other graph shows keratoconus eyes, and you can see there's much of a tail there. And what you can also see from that little table up there in the right there, you can see that on average a keratoconus eye is over 200 microns higher or deeper, or you want to, whatever way you want to say it, the sagittal height is higher for keratoconus eyes because of that protrusion, of course. So again, we can use this to define the normal versus the non-normal eye. And then we can further use this to see which lens we want to use. But let's take a look at the measurements options first. How can we best measure the ocular surface over that 50mm cord? Well, we were lucky to work with Jason Jetlicker on this one. Jason Jetlicker is from the Indiana University in the US. And he must be the luckiest guy alive in our industry and in our profession, because he has all these tools, all these instruments right available in the clinic at the school. So what we did, we asked him to measure one person, so it's an N of 1, but do it with all these different instruments. And let me walk you through that. He first used our current gold standard, the keratometer. And so for this particular patient, he measured the central curves and the HVID, both the horizontal and the oblique. And well, with simple calculations, you can then say this is the overall sagittal height of the eye. There's some software from different companies, for instance, that can do that for you. If you do that for an 11.9 diameter eye, this is what you'll end up with. 3,782 micron. Now, if you take all these instruments for that particular eye that Jason used, you take the average of that, how far off are we if we use this method? Not too far off, actually. It's within 100 microns. It's 87 to be exact, with this corneal diameter. And he used the oblique here. Now, he also measured the horizontal visual iris diameter, and he came down to 12.4, much more actually. If you do the math again, then we actually end up with 200 microns. So huge difference. So here's the lesson. It's not a bad method, but if you enter different numbers, and they are quite easily achieved with our current manual methods of measurement, you can be much off. 200 microns is probably clinically relevant, we think. So to put things a little bit in perspective, we did some calculations with different parameters. So for diameter, if you change the diameter by 0.5 millimeter, that is about 100 micron difference. And we think from 100 micron, it starts to become clinically relevant potentially. E-value is another one. 0.1 difference in E-value gives 100 micron difference. And with this calculation that I showed you, we just assumed the E-value is 0.5. We don't know that with a keratometer. And then the third one is central case itself. 0.15 millimeter difference will give you a 100 micron difference. So you know roughly what the variance is that you can get using this method. So let's shape it up a little bit. Let's add some technology to the table, quite literally actually. let's use corneal topography, and Jason happened to work with the MET one, so we're gonna use that one, and let's see what that instrument gives. So that you know, for this particular instrument, there's a special software that you can download. Ask your company for this instrument or any other instruments if they can do that, that can measure or calculate, I should say, the 50mm chord. And the MET one came up with 3,640 micron. That is pretty much on par, very close, about a 50 micron off, but pretty close. So good stuff. Now, I hear you think, some of you at least, the smart ones, this is a corneal topographer, so how can that give me the 50mm chord? It's not that complex actually, since we know from our studies that the shape out there is a tangent, is an angle. If you assume, and it is an assumption, but let's do that, that the peripheral cornea sort of extends out into the limbus and anterior sclera, you can use that information to sort of predict what's going to happen out there. And that's exactly what instruments like this do. And they do a pretty good job at that, like I said, predicting that from the peripheral corneal angle. It's a SAG calculator rather than a measurement, but larger studies, this is an N01, but larger studies have shown us that this instrument is actually not that far off from other instruments, like OCT. OCT is our go-to, or was our go-to instruments in the beginning. So 10 years ago we started looking at shape of the sclera, again for scleral lens research, and it's pretty simple to measure the sagittal height. And this one came down to 3,680 micron, and as you may expect, that is very much on par, if not is the gold standard almost, if you want, because you can actually see what you measure with this instrument. The downside though is that it's only one meridian, so you cannot look at vertical or oblique or whatever, but that is the number. Now, going to the next round, two instruments are specifically designed to measure ocular surfaces shape over a larger chord, and they both use their profilometers, and they both use fluorescein. Fluorescein is added to the eye as sort of a screen. You can project lines on that, and from these lines you can calculate height. So let's take a look at the first one that came into the market, the Eye Surface Profiler from the Netherlands, but no strings attached. What you can see in these beautiful pictures is that these instruments measure the sagittal height in different meridians, so that can be very useful. We'll come to that later. So as you might expect, this instrument is very much on par, 50mm compared to the average of all the instruments. And the other one is the SMAP from the US, Visionary Optics, and again, beautiful images, all designed for scleral lens fitting, and of course very much on par for this particular patient. And then the new kid on the block, the Pentacam CSP. It's a software and a hardware upgrade from the standard Pentacam. So you cannot do it with the standard one, but what it does, the CSP report gives us an overview of all these different sag heights in different meridians. Now the standard one gives the flat and the steep, so not the horizontal. So we're looking here at the 10-degree one, and it's pretty much in line with the rest. It may be a little bit off since we're not using the horizontal, but the 10-degree, but still very much in line for this particular patient. So what we can do with all these instruments is this: it's finding NEMOs. And NEMOs, of course, stands for normal eyes measured ocular surfaces. And then if we have a normal eye, again, let's see what room we have to play with our standard lenses, as opposed to sometimes if we don't have a NEMO, one of these NEMOs, we may have to go to a out of standard or a custom-made lens. So basically what this gives us is a bell curve, a beautiful bell curve, just like this one. It gives us a bell curve of normal eyes. The average is in the middle. We know the average eye is about 3,750 micron, and the ones on the right and the left are the ones we have to take care of. But the beauty is, we're in charge now. We're actually fitting lenses again based on, at least choosing lenses based on the ocular surface. And the normal eye would be somewhere between these black lines, somewhere between, well, let's say 3,500 and 4,000. That's where the range of normal eyes lay. So we know a thing or two actually about that ocular surface. So let's, oh wait, there's one thing we actually have to look at. It may be just a little bit more complex than just that. Let's fine-tune that a little bit. We may have to plane the wood a little bit, because as I said, in different meridians, different sag heights may be applicable. We're looking at the average over in the horizontal meridian, but what in the vertical or the oblique? Are there differences? Well, the thing is, nobody has really looked at it. So let's go back to the literature and try to sort of digest what's out there. This one is from Alessandro Consejo. She did the studies in Belgium. And well, she didn't look at 15 millimeters, so 7.5, but she did look at 7. So let's take a look at that. And what you can see from here, that the differences within, the average differences within one eye actually add up to 200, 240 micron, as you can see in the table here. On average, it doesn't look too bad actually. So what that says is that you can maybe use the horizontal sagittal height to sort of predict what the overall eye looks like. But let's take another look at this one. This is from Pacific University actually, and one of the studies that was done a little while back by Marcus Ritzman, and again, he actually looked at the 7.5 or 50 millimeter cord if you want. Not a huge group, 39 eyes, but still, as you can see, the average differences are not all that great. But the trick is, as Alessandra told me, of course, she's right, you have to look at individual eyes and not at the averages. So let's try to do that, and I'll take a shortcut for you. I'll make it a little bit simpler how we got there. But basically, this is the number. There could be within an individual eye, on average, for individual eyes, about 79 micron difference, so about 80 micron difference, and compared to the horizontal one. So what am I actually trying to say here? What I'm trying to say here is that, okay, if you have an instrument that can measure different meridians all the way around, perfect, use that. Because the lens is going to flex different in different meridians, and you probably want to go by the average from everything that you have. If you have an instrument that can only measure the horizontal, you're a little bit off by about 80 micron on average. It could be up to 200 micron basically. So it's not perfect, but it's not the end of the world either. So it's definitely better than nothing. But one thing we have to keep in mind, and we'll use it in the second part of the presentation too, how is that lens actually going to flex on the eye in these different meridians? It's not a two-dimensional, it surely is a three-dimensional exercise. One final thing on that before moving to the lenses, there may be differences in eye shape between Caucasians and Asians. I don't think it's that clinically relevant when it comes to soft lens fitting, but there are differences, so take a look at that if you're interested, that you may need to take into account. But overall, that's not the biggest of our issues. Alright, so let's go back to the puzzle. I think on the OCSAT part, we almost solved that part pretty much. Now let's take a look at the contact lens part. What do we know about that? Well, there's a couple of things we do know, there's a couple of things we don't know. So let's take a look at our tools more in depth, and specifically the tools to fit our lenses, which is the lenses itself. Now, based on that parameter of sag height, a couple of years ago we looked at, with an instrument from Optocraft from Germany, at a couple of lenses, and they're shown here in the graph, in the blue graph bars. It's a beautiful instrument. Here's a little movie clip of what they do and how they do it. Here they're showing the old method of viewing soft lenses, but that's not helping us very much in terms of measuring it. And also you have to control a lot of things, but the most important thing is the solution, of course, and the temperature of the solution. So this instrument, it's a very stable instrument. It stabilizes that temperature up to 0.0 whatever, very accurately. And of course you have to put the lens in a soft cell, which they do here, and then you can analyze all these parameters that are showing here, which is nice, but we're really looking at the or interested in the sagittal height of things. So with a side camera, they make an image view of that, and obviously you can measure the total sag height of that lens. And then you would have to subtract the thickness of the lens, which can be easily measured with a standard device. And then you'll have a beautiful overview of the sag heights of different lenses. And again, that's what we used initially. And a very useful instrument. It's bulky, it's big, it wouldn't fit into your practice, but certainly different companies around the world actually are working with it, the labs itself. Now, recently we worked with this device. It's from Optimac from the UK, so we're still staying in Europe. And what it is, it's an OCT device. So what it does, it's basically the Visanta or the Cirrus, but then in a lens measuring outfit. And it's roughly the same procedure, and the two key elements again is to get that temperature and that solution controlled, and of course there shouldn't be any movements and everything, because all that really influences the measurement. Again, it goes into a small wet cell. It's no rocket science in itself. It is, we used for our studies, we had used one investigator for all of our lenses. In fact, we did 44 lenses, some daily disposables, some reusables, and some toric lenses, and we measured them all like this. And you can even look at lens design and everything, but the one parameter we were interested in is the sag, and we measured all of them at 20 degrees, which is room temperature, and that's the ISO standard. But I'll get back to you on that temperature thing in just a little bit, because there's a little bit more to it actually. But we measured all these lenses, the same with the other instrument that I showed you, all in 20C. So we know a thing or two actually that we didn't know up to very recently, and we're actually updating that as we go along. But let's take a look at that batch of 44 lenses. First, I'm gonna sort of glance over it, because this is exactly the topic of last year's class, and I'm pretty sure all of that is still available through the CLASS website. So these are the daily disposables. You can see the beautiful linear increase. So we have some tools actually, from the flattest to the steepest. There is some room to play with if you want. These are the reusables, and you can see that there are differences between different lenses, different manufacturers, but even one 8.6 can be 200-300 microns different than the other 8.6. And same is true for torics. Again, we're updating that as we speak actually. Currently there's a new batch coming. So I'll show you the website where they go to at Pacific University, and if there are new lenses that are measured, like some myopia lenses we're measuring now, some multifocal lenses now, they should be up there soon, if not already. I told you I was going to come back to that issue of temperature. So what's going on with that? Well, we know from studies, and one particular study, this one from Graham Young, is that there is a pretty significant effect of temperature on soft contact lens diameter. And if you say diameter, you're saying other parameters as well, including the sag height. The problem is nobody has ever looked at sag height before. So again, we have to go back and try to fulfill the puzzle to the literature and see where we are with this particular parameter. We're going to look at diameter as sort of a surrogate first for sag. Now what happens, and I'm not sure if many eye care practitioners know this actually, but a soft lens shrinks on the eye because of the temperature difference. So if you go from 20 to 34, the lens actually shrinks. By how much? Well, what Graham Young did, he came up with a shrink factor. So he took the 34 Celsius data on diameter, and he divided that by the 20C data, and then you come up with a shrink factor, and the shrink factor was 0.98 on average. So actually it's not that huge. There was some variation between materials though, so some materials have more and others have less, as you can see, up to 0.95. So 0.95 would be 5% reduction, and 0.99 would mean, well, less than 1% actually. So there is a range between different materials. Ben Kuldrick with a poster at GSLS a couple of years ago looked at this too, and this is the only one that I know that actually took a quick look at sagittal depth or height as well. And as you can see, figure 6 and figure 9 showing the diameter decrease and the sag decrease. And it wasn't a huge batch of lenses, it was sort of a test or a trial, but it looks there is a linear relationship between the two. And I did the shrink factor based on Graham Young's work for that particular data set, and it was pretty close. So it was 0.98 on average, but again, there is some range between, well, it was actually smaller than in the, but of course there was less materials as well. All in all, it looks like there is such a thing as a shrink factor, and we have to take that into account. So probably a better way of doing things is to actually measure the 34 degrees Celsius, and that's exactly what we're doing with the new lenses that we're measuring, because those will give you the true sagittal height of the lens as they appear on the eye. Actually, for the newest lenses that we're doing 20 and 34 to look at the difference, and also the ISO standard is still 20, so we would still have to do that. One question my students came up is, well, what about eye temperature? Is there a lot of inflation of eye temperature if you go from a warm to a cold environment, from indoor to outdoor in the winter or things like that? And would that have an impact? And we looked at it, and I think we can safely say from the literature there's not a whole lot of influence of that. So the eye temp variation based on outside environmental temperature changes is probably not more than 1 or 2%. So in temperature, so I don't think that has a huge effect. If you go from 20 to 34, if that would be a difference on the eye, then we would have something to look at, but not with this. So let's leave that. We can sort of rest that portion. Do we have anything else in the drawer? Yes, one more thing. And it's not the most defined one, the fitting factor. So let's take a look at that particular drawer and see if we can make sense out of that. What do we mean with fitting factor? Well, there's other words, actually, terminology used for that, the flex factor or the fudge factor, and it's basically this. based on, at least best defined by another paper from Gray and Young, looking at the effect of, or the relationship, I should say, between soft lenses and the eye. Basically what he says, and we found the exact same thing in our studies, if you're going to put a soft lens on the eye, the soft lens has to be somewhat, and there you go, the somewhat is the fitting factor, steeper, and then the lens is going to flex. And if it flexes, forces have to go somewhere. They go outside and a little bit inside as well. But the outside actually causes a, believe it or not, an increase in diameter. So this sort of compensates to a degree, we don't know what degree, but to a degree the temperature change. So in essence, a soft lens has to be steep, it's going to flex on the eye, different meridian, it may flex differently. I don't want to make it too complex, but let's take a look at the average for now. It's going to flex by X, and then the lens diameter is going to increase by X. And how much is that? Well, it looks like it could be as much as 5% for the average eye with an average lens. That's an edge strain factor of 3%, as Graham Young just tried to explain there. If we use that as a model, and again, that's just a big if, but let's just assume that that is true for everything, but that's 5%. If we apply that to our data set, and we first do the recalculation based on 20 degrees versus on eye 34 degrees, and then apply that another 5% based on Graham Young's data, we're looking at about 180 micron. So roughly, and that, again, bear with me, that's a very rough number. The fitting factor could be somewhere in that range where the lens has to be 180 steeper in order to flex on the eye. If you don't have a fitting factor of, we think, somewhere between 100 and 300 micron, if you don't have that, and we've tried it, believe me, the lens is going to move all over the place. It's not going to be comfortable. It's going to cross the corneal borders, etc., etc. So the fitting factor is the one to be defined, and it's nice to have that number of 180, but it is, and he says that explicitly in the paper, it is material dependent. So the one thing we have to solve, the biggest one at least, in the puzzle, is looking at different materials and see how and how much they flex based on a couple of things, including their modulus. Now, a big giveaway, as you can see in the little graph on top, is that the water content and the modulus seem to be related to some degree. So that could be a first starting point, but unfortunately it's not that simple. But new technology and new research is going to come to the rescue here too, I think. This is another brilliant paper from the guys from Brisbane, Australia, and they developed this method to look at the modulus, the stiffness of different soft lens materials, and hopefully we can use this kind of technology to better understand how stiff a material is and how that may impact the amount of flexure or fudging or fitting, or it's an F factor, that's for sure, and that is something we have to define going forward, and that is the gap. We have to mind that little gap between the lens and the ocular surface, and quite literally, because both in terms of knowledge we have to mind the gap, and in terms of actually gap between those two. One study actually looked at if that lens is going to flex, is there such a thing as a post-lens tear film, and do we have to take that into account as well? OCT images of lenses on the eye show us that there's hardly anything. It's maybe a micron or two between the lens and the ocular surface in different areas. Not something to be particularly worried about. So that is not where the gap is. It's more in that fitting factor and how to incorporate it. And I like simple messages, but that part may not be simple. That fitting factor, how much steeper basically are you going to fit that lens on eye temperature than the ocular surface. If you have all that information, that number could be dependent on that particular lens and even on lens design as well. So that's the one we're going to work on in the next year or so. Hope to report back to you in class 2021 with even more on this topic that is very dear to my heart, and I think it's quite essential, to be quite frank, for our industry to look at that in depth. I have a little newsletter on soft specialty lenses, actually supported by Contamac. It comes out every month. If you want to sign up for that, just Google Soft Special Edition. And we've talked about soft lenses obviously in about the decade of scleral lenses, which was basically the last year. But in a recent column, I sort of predicted, if you want, and maybe I'm just hoping it, but that the next decade could be, and should be maybe, the decade of soft specialty lenses. When it comes to myopia, we have so much to learn and we can do so much more than we're doing right now. But we first have to understand what we're actually doing when we're fitting a soft lens. So I think, going back to the barn, I think it's we got to get our hands dirty and really start working with all that information we have, and ideally with some of the technology that I showed you, and that way we can solve that soft lens dilemma and maybe make it a little bit less of a commodity but more the medical advice that it actually is. How can we do that? How can we improve soft lens fitting? I've showed the flowchart last year. We got to go through all that. We got to look for normal eyes, and if we have them, then we can go to SAG story, but there's material as well, there's other variables. If we don't have NEMOs, we may have to go to, if we have a unique eye shape, extended parameters and custom-made lenses. So there's a lot of opportunities there, and all these lenses are there. We actually have the tools to do better. It's just knowing when to use them, basically. One thing is for sure in my mind, it has to go beyond base curve in order to solve that puzzle. First starting point, maybe those graphs that I showed you. Here's a QR code that you can scan. If you do that, it will take you directly to the Pacific University website, where Mari Fujimoto is sort of gathering all the information on SAG heights that we have and the ones we're doing now and in the future. So keep an eye out for that. You can just scan that and we'll take you there, and or I will ask the organizers to put it on the website as well. As a very final slide, we looked at dropout rates, and there's a lot of talk about dropouts, and I don't want to get into that too much at the end of this long presentation with a lot of information. But one more number I want to show you, and that's the number of 3.5%. Philip Morgan has predicted that if we can reduce the dropout rate on a yearly basis by 3 to 4%, we can double the amount of lens wearers, between now and 2040. Isn't that amazing? And I think, and we think, the team at Pacific, by just looking at lens design, and I know it's way more complex than just that, but let's just single that one out, we should be able to do better and maybe reduce the dropout rate by 3-4% just based on lens fit. So that is the hope, and that is the message that I wanted to give in this workshop, on an advanced course for sure, on something that seems very basic. Thank you very much.